move on to the talk of Alberto Baiardi, and he's going to tell us about his recent developments in the field of DMRG for study of vibrational dynamics and nonequilibrium dynamics.
Share first. Okay, proceed. Yeah. Right.
Yeah, perfect. 20 minutes.
Okay, perfect. So thanks for having me here. It's my first actually in-person OpenMolcas meeting. So as other people said this morning, I guess this is the first real occasion to meet. I'm a postdoc at ETH Zurich in the group of Markus Reiher. And let's say what we do is we study methods based on the density matrix renormalization group algorithm, DMRG, applying it to many potential interesting molecular simulation fields. And the DMRG was kind of popping up already in the talks, but I will kind of just give a few, let's say, insight about the idea that underlies the methods. In a nutshell, what DMRG is about is kind of an efficient way of solving the full configuration interaction problem. And so it kind of, the aim is the same as other methods that were introduced in this lecture, in this conference, like full CI quantum Monte Carlo, HIPAT-CI, different flavor of selected CI. And so what we aim at doing is fight kind of the exponential cost of the full configuration interaction method. And just to mention it, it's this exponential cost and why it's so difficult to do kind of exact molecular simulation with full CI lies in the fact that basically we are using as building blocks for expressing a many-body wave function, which is something complex in terms of very simple one-particle basis, which are the orbitals, for instance. Although kind of this idea is not just limited to electronic structure problems, as I will mention later. And the way in which kind of DMRG fights this exponential speedup is applying this exponential cost, is applying tensor factorization technique. So it kind of interprets the wave function as a tensor, and so you can imagine it like as a big image, and then applies compression techniques to reduce the size of this image, and so makes it possible to store the wave function, for instance, in the laptop, and so do simulation with it. And graphically, this is represented there in the right part of the slide, where a huge tensor, which represents the full CI wave function, is decomposed in smaller tensors represented by green dots, by green circles. What's nice about DMRG is that there is a single it's a rather, let's say, simulation-friendly factorization, because there is a single parameter that tunes basically how large those tensors are. And so on the one hand, how close I will be to the full CI wave function, but on the other hand, how, let's say, how much I'm compressing. So ideally, I would like to compress a lot, but don't lose accuracy in my simulation. So in the recent years, so let's say, applying DMRG to molecular science is definitely not, let's say, a new idea that we introduced. It's something that has been around since like roughly 20 years, I would say. And it has become nowadays an established method for calculating ground state electronic energies. So basically, a single point of the potential energy surface. What we did is try to extend it beyond that. And so what here, we used it, for instance, for calculating potential energy surfaces. And so just to mention, I think, gradients of ground state and also of excited state. So trying to kind of use DMRG and bring it towards the application in photochemistry. Another field we looked into is using DMRG not only for like solving the electronic problem, but also for solving the nuclear one. So, for example, calculating anharmonic vibrational energies for having then application to spectroscopy, but also looking at dynamical processes. So, with a direct application in ultrafast science, for instance. So using DMRG for solving the quantum dynamics problem. We also looked at something which kind of relates to the last talk, which is using DMRG to kind of couple electronic and nuclear processes. So let's say without assuming the Born-Oppenheimer approximation. So we apply DMRG to pre-Born-Oppenheimer Hamiltonians, which were kind of, along the line of the method that were like Darello, for instance, by Sharon Meshif and also Ardi-Gross, as it was mentioned in the previous talk. This is kind of the big picture. Last OpenMolcas workshop, I was focusing more on the dynamics part. So today I decided to speak about two very recent developments we have been doing. One concerning the targeting of excited states, which is a challenge for the DMRG, and we think we found a nice method to solve this problem. And also concerning, let's say, accurate electronic structure calculation based on the transcorrelated idea that was already introduced by other talks in the first day of the conference. So I'll get started with the first topic, so the excited state calculations. And so what we aim at is using the DMRG not just for calculating the ground state energy, so the lowest eigenfunction of the full CI Hamiltonian, but to calculate full spectra of eigenstates, or also maybe better selected electronic states, which may be selected excited states, sorry, which may be low energy, which would mean for the electronic structure case, for instance, a valence excitation. But for the vibrational case would mean, for example, the fundamental excitation of a given mode. But ideally, we would like also to explore high energy excitations, both for electronic and for vibrational problems. And for electronic properties, of course, the electronic case, the application field that one would have in mind is, for example, X-ray spectroscopy that was covered by many talks in this during this conference. And why is it difficult to kind of apply the DMRG to calculate excited states? And the reason is that inherently, the DMRG is a variational method that optimizes the kind of green bubble I showed before based on the variational principle. And it does it in an iterative way, which is inherently state specific. In a sense, it's inherently tailored for calculating ground state wave functions. One can, in principle, target excited state by doing constraint optimizations of them on target one state after each other. But this procedure becomes quickly tedious, especially if you want to go very high in energy. In the recent years, we used methods based on the auxiliary operator to target directly excited state. This goes along the line of what Giovanni spoke about this morning. But instead of having a penalty that kind of make us prefer a state of a given symmetry, of a given spin symmetry, what we do here is that we modify the Hamiltonian by shifting it and inverting it, for instance, such that I can select a shift parameter, modify the Hamiltonian, and then I can apply the DMRG to this auxiliary operator such that the ground state is the excited state which is the closest to the shift parameter. This kind of worked, but it's still not ideal because for, let's say, technicalities that I will just keep for the here, because applying the DMRG to these auxiliary operators is complex. In a sense, the efficiency of the DMRG is kind of killed. If one is kind of compromised, at least, if one applies that to auxiliary operators like that. So our solution is an algorithm that actually is around since 13 years. In the physics community, at least from what we saw, is not that used in quantum chemistry, although I think it has huge potential in this field. And it was originally introduced by the group of Polizzi in the States. And the idea is, instead of saying, okay, I want to target an excited state with that energy, let's assume we want to calculate all the excited states that are given in a given energy range, here represented in red. Let's assume there are 5 states there. Well, if I had the wave function of those states, I could construct a projector operator onto that subspace. Then I could simply just generate 5 random wave functions, trial, project them onto the subspace, and this would give me the eigenstate I wanted with a given linear combination that I can disentangle by diagonalizing the Hamiltonian in this subspace. This is, of course, a chicken and egg problem, because if I had the wave function, I would not need to diagonalize the Hamiltonian for getting the wave function themselves. But here comes the smart idea that underlies this algorithm, which is one can show that one can rewrite this projector as a complex integral, or an integral in a complex plane of this operator, which is basically the green function of the Newtonian. So now the specific kind of wave function are disappearing from the expression, from the formula given the projector. But again, to apply this onto a given trial wave function, I would need to invert the Hamiltonian, which is something hard, and calculate an integral. The second key idea is that one can approximate this integral numerically with, for example, a Gauss-Hermite quadrature. And so decompose the projector as sum of terms. And so if I wanted to apply this operator onto a trial wave function, what I need to do is just apply the inverse operator on the trial wave function for a number of time which is equal to the number of points of the quadrature, and then sum together the results. The third key idea is not to solve, so basically applying the inverse operator amounts to solving a linear system, but one can not solve the system exactly, but doing it iteratively with a Davidson-like procedure. And this won't be exact in a sense I'm approximating the projector, but if I'm repeating the algorithm many times, eventually will converge to the target eigenstates. So what I need to do is basically generate a random wave function, apply this approximate projector many times up to the point where it's kind of converged. This is just the fist algorithm. What we did is kind of DMRG fist, where the key difference is that every wave function is not a full CI wave function, but is encoded as a matrix for that state. But the key idea is just the same. What are the advantages? The advantages is that I don't have, so as you see, basically here, the shift that are appearing here, something which is defined by the quadrature, and so they're not defined a priori. So I don't have to say specifically where I want to look at the excited state. I just have to give a range. And then for a let's say, accurate enough grid, the nodes are selected by the algorithm, not by me. The algorithm is parallelizable. I can explore different energy regions independently. And one does not have to construct complex auxiliary operators, which are potentially difficult to apply to DMRG. So I'm going to show some results about vibrational calculation, although we are in the process of trying to make it more general and make it applicable to all possible, all Hamiltonians who study with DMRG. And those are the vibrational states of ethylene, which we chose because there were also IFBAT-CI reference data we could take as a reference. And the take-home message is that although this is a molecule with 20 modes, so it would be kind of a CAS 12 modes, or it would be a CAS 12-12, the convergence with the bond dimension is rather fast, which basically says that calculation like that can be done very quickly, which also points to the fact that extending it to electronic structure calculation should be and should work well. And the good news is that one can also look at high energy states, which in vibrational calculation are things which are, let's say, a frequency of thousands of intercentimeters, here represented by the CH stretching of ethylene. Here I'm representing basically the energy that I'm getting from the fist iteration as a function of the fist iteration, and this is the reference energy I get at the end. And as you see, basically the convergence to the final energy is very smooth and very quick. So it's enough to do 1-2 iterations to get a converged result. So I believe that this is something which, in general, I believe in quantum chemistry could be exploited more, but especially for DMRG, where this problem of doing excited state calculation is crucial, this is something that can really help us in the future. Of course, we are still working on automating everything, but ideally one can really think of algorithm where you cut your energy space in different pieces and the algorithm explore all the excitation energies for you. So going to the second topic, the second topic, a lot of has already been said in general, let's say in previous talk. So the idea that we want to exploit, and so switching kind of fields, is now looking at another problem, which is try to kind of attack the problem of dynamical correlation in the DMRG calculation via the transcorrelated model. So the transcorrelated idea, which has been already discussed in the first day is to take a wave function ansatz, which is composed by a given wave function. In our case, it will be the matrix product state, so the DMRG wave function times a correlator. The correlator should kind of take care of the fact that should enforce the correct short-range structure of the Hamiltonian, which is something that DMRG would not be able to kind of represent efficiently. And so the idea is that if we optimize the DMRG wave function in the presence of the correlator, the DMRG wave function can be kept much more compact. The work that inspired us was the series of papers that were done in Stuttgart by the group of Anelavi that showed that actually by a transcorrelation, one can speed up full CI quantum Monte Carlo calculation, and we want to kind of to add another piece to the puzzle of these transcorrelated methods that are emerging and seems to be very powerful for accurate electronic structure calculation. Of course, the key problem here is that the Hamiltonian, so the idea is to carry out the optimization by revolving the correlator in the operator, which is now similarly transformed, which means it's non-Hermitian, which means that one cannot apply naively the variational principle. How do we solve that with DMRG? Well, there is a orthogonal formulation of DMRG, which was proposed actually quite a long time, like 15 years ago by the group of Garnet Chan. But we didn't go for it because in this case, one would need to represent as matrix product state both the left and the right eigenvector of the Hamiltonian. And we expect actually, and this was again proven numerically in this work in the field of full CI quantum Monte Carlo, that in transcorrelation there is an imbalance between the left and right eigenvectors where one becomes less correlated and one becomes more correlated. So we would like just to work with the less correlated wave function because this is something which we can represent better with DMRG. And we do that in the same way as it's done in transcorrelated full CI quantum Monte Carlo, so by imaginary time propagation. But in our case, we do it deterministically. So we don't do it stochastically, but we do it deterministically with an algorithm, and I will just skip some details here, which goes under the name of tangent-based DMRG. And the idea is just that one solves the time-dependent Schrodinger equation by plugging the factorization in the time-dependent Schrodinger equation with imaginary time. The advantage is that of this framework is that one can basically propagate every single component one after each other, which is nice because it's very similar to the way in which DMRG optimizes wave function. Just jumping to some results, I will just first mention that thanks to the work of a collaborator at the University of Warsaw, Michał Leziuk, we applied the density fitting approximation to simplify the integrals entering the transcorrelated Hamiltonian. I will skip the details that you can find in the paper that just appeared in GCTC. I will just say that we show that this is robust and efficient. Just two results. I will first show a result of an atomic system. As you see, if you compare conventional DMRG to the transcorrelated DMRG, the last line, you see that there is an enhancement of the convergence, or like a lower enhancement of the convergence to complete basis set limit, which is what we would expect for an explicitly correlated method as the transcorrelated one. We saw basically the same also for the molecular system. This is just the hydrogen molecule, where you see that there is a constant getting closer to the reference curve, which has been calculated basically with numerical methods, going from conventional DMRG to the transcorrelated case. So the convergence to the complete basis set limit is faster. There are still some limits, which I highlight here for the beryllium dimer case. Here, the dotted lines are conventional DMRG, the solid lines are transcorrelated DMRG. And as you see, this is the exact experimentally kind of determined curve, which we would aim at. If we do transcorrelation, actually the barrier becomes better, but we have a worse agreement here. Due to the fact that we are using a relatively small basis set, we would like to use at least a triple basis set, triple zeta basis set for the transcorrelated calculation, but this is something which costs too much because the Hamiltonian is just too large. The transcorrelated method, as was mentioned in some talk before, contains a three-body operator, which is very difficult to manage. And so we are trying to compress it in order to go to higher and larger basis set. I will just stop here. just mention the code where we do all of this. We are currently making effort to make it more efficient, more usable. So feel free to ask and come back to complain in case something that does not work. We will do our best to fix it. And I will mention collaborators that were involved at different levels to this project. I hope I'm not too late. And I will stop here. And thank you for your attention.
Thank you very much, Alberto. So we have one question. One question. So, yeah, please.
I was wondering how you choose your n value.
Yeah, you mean, for instance, so here we did other calculation with other m values, and we monitor the convergence. And so basically, for example, the transcorrelated calculation with 10 equals for 450, we have it, and it's just on top of the 300 calculation. What you observe actually is also that by a transcorrelation, since we put a bit of the correlation in the correlator, the M convergence is faster because the DMRG has to do less job in a sense, and so can be more, the wave function can be more compact.
Okay, thank you very much, Alberto.